Okay, hi everyone. My name is Jacek Enczura. I'm tech lead at J&X, and today I'd like to introduce you to blockchain and Bitcoin. What is it, how it was created, and how to use it. At the end, I'd like to show you a live demo and how to and show you how to write a basic app that runs on Ethereum blockchain, and you will see how easy it is to use blockchain. Okay, before we can even talk about Bitcoin, we need to get some basics about cryptography. We cannot talk about blockchain without basic understanding of things like hash, symmetric, asymmetric encryption. And please remember, I will use quite a lot of simplification in this talk because introduction to cryptography takes at least one semester at the university, and I've got 40 minutes for the presentation. So be mind, I will use quite a lot of simplification, and I will tell you where is deadly simplification that might cause you to lose a lot of money in cryptocurrencies. Okay, let's start from hash function. Probably all of you, since you are all engineers, are familiar with MD5 or SHA-256. Hash function transforms into output data of a fixed finite length. So input the text of I don't know some Faust of Wolfgang Goethe or any book can be transformed into a fixed size string. Always the same length, so no matter if the string is shorter or longer than 64 characters, it will be always the same. It's really important in hash function that we can't say anything about input string and predict what input string was. So basing on this string here, we cannot know, or we shouldn't know, that this string was created by hashing the string input. And a good hash function prevents R for creating hash collisions. Have you ever heard about hash collisions?
Yes.
Okay, good. So for those who didn't answer, since we are transforming a big string into smaller string, it's certain that at some point two hashes might be the same. So, but good hash function prohibit us for and makes it impossible to predict which string was created, what was fed to this hash function at the input. So that's really important, that we cannot predict that C96 was created by hashing a string input. And what hash function is used for? Most importantly, hash function is used for something like a proof of existence. So imagine we are writing a book and we want to release this book next year, but the book is written right now. I can hash this book, so I can feed this whole book into hash function and get a string of finite size, and I can use something like Twitter or some place stored somewhere that I know that will survive 1 year or I don't know 10 years. I post it, and it's a proof that at that point of time I wrote this book, and the content of this book was not changed. Another use case for hashes is a fast integrity check and fast identification of corrupted data. We can think there are four pieces of data A, B, C, D. and we create a Merkle tree, which is the tree of hashes. So we hash data A, hash data B, hash data C, hash data D, and we get those 4 hashes. And then we hash those 2 hashes together. So we take as an input hash 1 and hash 2, and we hash it together. We have hash AB, and we do the same with hash C and D. We've got hash CD, and then we hash A, B, C, D, and we have a root hash. And then whenever something was changed in data B, hash B will be different, hash AB will be different, and the root hash will be different. So it's super easy to quickly check that one piece of data was corrupted and check the integrity of data. Now, do you have in mind any very popular use case in programming world for hashes? Do you know where they are super used and all of us as developers use it every day multiple times?
Yeah, authentication like JWT.
Yes, JWT token, but it's rather encryption, because you can get from JWT token you can get what are the claims in the token. So it's encryption, it's not hashing. Hashing is used in Git. Git is the most basic
password
blockchain. So in Git we've got a commit, and in the commit we've got a hash of the previous commit or of the state before that. And Git is actually a basic blockchain. So since we're talking about blockchains, let's create a blockchain using hashes. So blockchain is a set of hashes joined together. So let's create an initial block. This is the first block of my blockchain. We take this string, we hash it. So this is the string and this is the hash of the string. What's super important when it comes to hashes is that any change, changing, adding F is changing the hash completely. You can see that ending was 2AB5 and with double F is DA38, or changing lower O to bigger O, it's as well changing the whole hash. So it's super important that any little change in the input data is creating completely different hash at the output. So let's take that hash and let's create our first block. So this is our first block. In the second block, let's add some string. Guys, I need some example. Type something in the chat, whatever we can use to create a blockchain. Can someone type something in the chat, please? Okay, blah. Blah is another text. So we take the previous hash of the initial block and we take blah that David wrote. We take this as the whole block, we hash it, and that's the new hash. So let's create new block. We put the hash of the previous block on the top, and we take another string. So we take another string, which is something in the chat by Bianca. We take this two, we hash it, we take the new string, we put it on top of the new block, and I can put here my name, Jacek Janczura. We can hash it, and that's the hash of this block. And that's the hash. So, why it's important? Imagine I'm changing something in the first block. If I change something in this block, this hash will be different, because that's how hash works. If I change anything in the input data, the hash will be completely different. So even though I added this string blah, this hash will be different as well. This hash will be different, and this hash will be different. So it's super easy to check that I modified something. If I modify a string in the third block, so something in the chat, this hash will be different, and this hash will be different. So it's super easy to check which block was modified and where someone tried to corrupt the data. So that's super easy. We created blockchain, and that's it. Thank you very much. That's the end of the presentation. Of course not. So let's sum up. What is blockchain? Blockchain is append-only registry. You can add data, but you cannot remove the data without leaving a trace, which means if I add here something important in the chat and I try to hash it, you can see that the hash of this string is not equal to this hash. So it's super easy to detect the trace when someone corrupted the data, and it's not possible to modify blockchain without rewriting the whole previous blocks. You can verify integrity of blockchain yourself. It's super easy, but you need to access to the full data. So you need to access to the whole blockchain and the previous blocks to verify the integrity. And that's why blockchain, in order to verify the transactions, blockchain is growing. And currently, Bitcoin blockchain, if you want to get the whole transaction log and all blocks, it takes 311 gigabytes. And there are 660,000 blocks in Bitcoin in the beginning of 2022, of course. And in case of Bitcoin, in one block, you've got 1.5 to 2,000 transactions. Before I tell you what transaction is, let's focus on a next example, which next important word, which are peer-to-peer networks. Do you have any questions so far?
No question.
Okay, good. So, peer-to-peer networks. In peer-to-peer networks, we no longer talk about servers and clients. In contrary to the centralized server, where we have one server and we have multiple clients, in peer-to-peer network, all peers, because there are no longer servers, are equal. So notation of clients and servers doesn't apply. That's why we use peers, because peer can serve as a server and a client simultaneously. Peer-to-peer network, the best example are torrents. So whenever you own a piece of data, you share this data with other participants of the network, and in case you want to download the piece of data, you download different pieces from different computers, so it's faster. Very important, peer-to-peer networks. Peer-to-peer network is a distributed network. So in case this peer is down, I can download the piece of data from other peers that are in the network. It's really important. In contrary to the centralized architecture, where whenever the server is down, we can no longer access the data. Okay, let's talk about another keyword, which is centralized registry. We all are familiar with centralized banks as a mean of centralized trust. We all have different bank accounts, and with our money, whenever we transfer money to the bank, we trust that the bank keep a record of our money. So whenever I forget how much money I have, I can always ask the bank, dear bank, how much money do I have? And the bank will tell me. And the bank is a central place. Whenever I'm doing something with my money, a bank keeps track of my what the contents of my account is. So the bank keeps the track of A deposited $1,000, D took $15,000 credit, a bank charged D $100 with a loan interest, and C deposited $10,000. So this is a centralized registry. We've got one centralized institution whom we trust and who keeps track of our finances. Now, distributed registry. Imagine a group of anarchists. Different anarchists don't want to use bank, but they somehow want to keep track on their expenses. So let's imagine we've got anarchists A, B, C, D, E, F, and they all have the same notebooks. The piece of paper with the same with multiple papers and with the same number of rows in each paper. And those anarchists make a transaction. Whenever they make a transaction, anarchist A shouts, "I am sending the $10." And all anarchists A, B, C, D, E, F note it down in their notebook. A sent the $10. Then D is shouting, "I'm sending E $15." And all anarchists keep track and write down D sent E $15, and so on and so forth. When we, since all of them have the same notebook, they write down all the transactions on the same pieces of paper, and which means that at the same time for everyone, this piece of paper will end. Those anarchists are really good in math. They take the transactions from the whole page, they hash them, so it's a proof that no one can modify the transactions. Then they turn the page to the new page. They put the hash of the previous page on top, and they start writing down the transactions. C sent F $5. So all of them note it down. And when the page ends, they make a hash and turn the page to a new page. So this is basically a block. These blocks are joined together by hashes. So the hash of the previous block is on top of the new block of the transaction. So this is an example of a very basic blockchain with the transactions. The question is, what happens when a new person joins? So how do we handle this scenario when we've got fifth or sixth anarchists who want to join the circle and participate and send transactions with each other? If you take if you rewrite the whole pages from one person, there might be a threat that this person modified something. So whenever you are joining, you see modified balances. So the solution for it is quite easy. We take one page from one person and from a different person, and we check the hashes ourselves. If a hash doesn't work, so if some person modified something, we ask another peer, another anarchist for that page. And the network works until 51% of anarchists are trustworthy, and that trustworthiness here is based that all of them want this system to work. Okay. Any questions so far regarding distributed registry?
Hi, I have a question.
Sure.
So, if you want to trace back, is there any way that we can trace back that which person has modified, or what's that process is about?
Yeah, obviously. It's super easy. So if someone modified something in a blockchain, the page of this person will be different. So until 51% of those participants, so of those people, have correct pages, didn't make a mistake, didn't fake the transactions, the system works.
So,
And with the integrity check. So we just hash it and check if this hash is equal, if the hash of this block is equal to the hashes that another users have. If someone has a different hash, it means this person modified something. And he no longer can participate because on top of the blockchain, he will have, so if he modified C cent F, not $5 but $10, this hash will be different. This hash, which means this hash will be different. So it means the whole next blocks of this person will be corrupted. So the hashes won't be equal, which means the pages of this person won't be taken into account.
okay, so how this works in a real-time scenario, like when we have, you said for the Bitcoin example, we have thousands of transactions going on. So how we check for all of them? For the block?
I will answer to that question later. So before the peer, before a guy who is writing down those transactions adds the transaction to their block, they check if the person D actually had on their account $15. If not, they just discard the transaction because it means that D wanted to fake him. And if he adds the transaction that is not trustworthy and he creates this new block, other peers will very easily detect that you've got something wrong in here, you're not counted in.
Okay.
Does it answer your question? Yes. Okay, any other questions?
Hello, Joseph.
Yeah.
So I want to ask, like, when is the corrupt thing? Like, we can reverse track to that when the corrupt is matched. Then till then, the matching is correct, and before that we have the corruption, right?
Yeah.
Okay.
So until we changed something in the chat to something important in the chat, that was the hash, and the new block was created using this hash. So when we change something in this string, modify the transaction, the top level hash of this block will be different, will be this, which means this hash will be different. So it's super easy and fast to detect when and where something was corrupted.
Thank you.
Okay. Two very, very important things: asymmetric encryption and symmetric encryption. Symmetric encryption is the basic example of key in the door. We've got one key to encrypt and decrypt the data. So IS-256 is an example of algorithm where we use a specific cryptography. Here are some simplification, of course, because I don't have time to explain this. But here, with using symmetric encryption, we've got just one key which allows me to encrypt and decrypt the data. In case of asymmetric encryption, we use one key to encrypt the data and the other key to decrypt the data. Where do we use it? Are you familiar with SSH?
Yeah, somewhat, you can say.
SSH or TLS or any kind of or this little icon here, this is a proof that whenever I'm doing in my browser, this is encrypted with my private key sent somewhere, and the recipient of this data is as well Google.com, not anyone else, and only Google can decrypt whatever I'm doing on the website. And I'm sure that whatever someone is showing me here is Google because I can check that using asymmetric encryption. So in asymmetric encryption, we've got two pair of keys, one for encrypting the data, the other one for decrypting. We can call it public and private key because private key can be used only for encryption, and I can share public key with whoever I want, and anyone who owns my public key can check that so the owner of the private key encrypted the data, and this person can decrypt the data and prove that I'm the owner of the private key. And as long as I don't disclose my private key, I can verify myself because I'm the only owner of this key. Let me show you an example. cd.ssh. Are you familiar with this folder on your machines? .ssh.
Yes.
.ssh keeps track on public and private keys. I can show how the public key looks like. Of course, I won't share the private key, but we can create one. So this is a public key. This key can be shared, for example, with my GitHub account. So, I share this key with GitHub, and whatever I do on my machine, I send the changes to GitHub. I use my private key to encrypt the changes, and GitHub can verify that I used my public private key to encrypt the changes, and GitHub can use my public key to decrypt them. That moves us to another important thing, which is signature. What is signature? So we know already a hash. So instead of encrypting the whole data that I'm changing, encryption is always much longer and much more time-consuming than hashing. Hashing is super fast. Encryption is time-consuming. So instead of encrypting the data, in order to prove that I wrote this data, I can hash the data. So I have the hash of the data, and I can use my private key to encrypt this hash. So I've got an encrypted hash of this data, and then I can share this hash with someone else. And this hash is a proof. If someone owns my public key, this person can check that this data was encrypted by someone who owns a private key to that public key. Do you get it? Or let's create some minus TRSA, something like that. Yeah. Okay, I created those two keys, and now I can share them with you. Test_RSA. This is private key. This key is longer than a public key, and this key is used for encrypting a hash. And this is a public key. I share this public key with anyone I want. I use my private key to encrypt the data, and whoever owns a public key can verify. They don't know the private key, but they can verify that this data was encrypted by someone who owns the private key to that public key. So it's super easy to check that. I can always check that whenever data was encrypted with a private key, and I know public key to that private key, I can check that this person encrypted some data. Do you understand it, or shall I give you some other example?
We understand that, but Jessica, I have a question. Like when we connect to when we connect to a SSH to a computer, so we use the same concept, right?
Sorry?
When we connect to a computer using SSH, like when we connect to a Linux server using SSH.
It's the same concept. So you use your private key to encrypt piece of data So the server sends you a challenge. Server sends you if you are Anush, encrypt for me this random string. Then you use your private key. You encrypt this string. You send it back to the server. Dear server, I'm Anush. I encrypted this your string with my private key. Verify it, and then the server checks the signature with your public key and verifies. Okay, this public key corresponds to that encrypted data, which means that the guy who owns a private key encrypted this data.
Okay, I understand that. Thank you, sir.
And then you establish a secured connection with the server, because server knows your public key. They don't know your private key, but by knowing your public key, it's super easy to verify that something was encrypted using this specific private key that corresponds to that public key. So it's important that in asymmetric encryption, the keys are always in pair, public and private key. And it's super easy to check that some data was encrypted with private key, even though you don't know what the private key is. By only having public key, you can check that. So, coming back to blockchain, deadly simplifications, guys. This is not 100% true. In blockchain, public key can be assigned as a wallet address. So, blockchain account number is a public key. In banking, we've got a SEPA number of my bank account. In blockchain, you've got just a public key. So whenever I send to that public key, we can always access the data with a private key. In order to send a transaction, we need private key because we need a signature. And in order to send a transaction, we need a recipient wallet address, which means a wallet public key of the recipient. Let me show you how it works. This is a test network. So whenever you try to work with blockchain, in blockchain, this is an example of Ethereum. In Ethereum, there are test networks. Don't use at the beginning public network, because on public network, you operate on real money, real currencies. In test networks, there are multiple different test networks. They differ with different things. Some are faster, some are slower, some use different algorithms. In test networks, you use a fake Ethereum, fake Ethers, fake currency. So that's why I have 100 Ethers. If I have 100 Ethers, currently, that would be 3,000, 30,000, 300,000, $3 million, if I'm not mistaken. Of course, this is fake Ethereum, so it's not. Let me account one. In account one, I've got 100 Ethers, and in account two, I've got 6 fake Ethers. This is a public key. I can show you how it looks. This is a public key of that account, and this public key is public. So whenever I want to send something to some person, I send to that account. So let's send some Ethers. When I send, I need to paste the recipient public key. So I'm sending, let's say, 10 Ethers, 10 fake Ethers to that address. I'm sending 10 Ethers, then I click next. And then what is happening here? I see the pricing fees, I see how much money I'm sending, and when I'm clicking confirm, I'm making a signature, which means I'm signing this transaction with the private key of account one. Now the transaction is signed, is sent to the blockchain, then the peers check if I had 10 Ethers. If I had 10 Ethers, they will add it to the blockchain, and on account 2, I will have no longer 6 Ethers, I will have 16. It takes some time. Transaction was sent. I now have 90, and in new account, I got 16. And this is where we use signatures. So in this distributed registry, we no longer talk about people, A, B, C, D, E, F. We talk about addresses, public keys, public key address. This is important. And when we are going closer to Bitcoin, let's explain difference between Bitcoin capital letter and Bitcoin lower letter. Bitcoin with capital letter is a cryptocurrency's blockchain based on peer-to-peer network. Bitcoin with small letter is a token in Bitcoin network, monetary unit. This Bitcoin, one Bitcoin, divides into smaller pieces that are called Satoshi. So 1 to the power of 12, 10 to the power of minus 12. So we've got 1.000001, and this is 1 Satoshi. So Bitcoin can be divided, like a euro can be divided into cents. Bitcoin can be divided to 100,000 pieces. The Ethereum can be divided to 30 more pieces. So to 100 billion pieces, something like that. And we've got different blockchains. So, for example, in case of Ethereum, Ethereum is a blockchain, but the name of the currency is Ether. Just out of
Sorry, Jacek.
Yeah.
Is it Satoshi like gas in Ethereum?
No. Satoshi is like cent in euro.
Oh, okay.
So 10 million Satoshi is equal to 1 Bitcoin. 100 million Satoshi is 1 Bitcoin. So it means that 1 Satoshi is equal to 0.000000001 Bitcoin. Like euro and cents. Do you have any other questions, guys? Okay.
No.
Okay. So you've seen when I sent some ethers. You've seen that there was something called transaction fee. There is a graph that shows the estimated time per transaction fee in a Bitcoin network. If I don't, because why someone would add your transaction to the blockchain? The whole network is based on grid, right? So the more Satoshi per transaction you pay, the more likely is that someone will who is adding this transaction, so the peer of the network will add your transaction to the network. So the more you pay, the faster your transaction will get in the network. So there is this graph. So if transaction fee is 0, your transaction will never be added to the blockchain. The estimated time is infinity. If you pay 30 Satoshi, it's something like 5 years. If you pay, for example, 500 Satoshi, it's almost instantly. If you pay 390 Satoshi, it's something like 0 to 4 minutes. So you don't need to be a peer in the network. You can just approach the group of the guys and tell them, guys, I want you to keep track of my transaction. I'm sending Fuet 10 Bitcoins. And I will pay, if someone adds this, I will pay you some money. Now, proof of work and consensus. So how do we decide who adds new blocks? So in distributed registry, we had those blocks. They were joined by hash, and all people were participating in it. But since the work is based on grid, how do we assure that people who are keeping track don't resign? There needs to be a reward. If you are participating in the network, you should be rewarded because you keep track and you keep this 300 gigabytes of data on your drives, and you before you add a new transaction, you actually check if this person, you check the transaction and you do work. So there needs to be reward. Currently, the reward in Bitcoin is 6.9 Bitcoin for adding a block. What it means adding a block, I will explain in a second. So, how can we assure that all participants in the network has the same transactions and the same blockchain? Instead of all of them keeping the track of all the transactions, we can say that one person who does something, solve some puzzle, is the best or whatever, adds a new block and share this block with all other participants. All other participants check the transactions one by one, and this person is rewarded because he added this block. How do we choose this person? We can think about most power in the network. So whoever has the most power should be allowed to add the new transactions. But this ends up in a problem where only this person is rewarded, and this person can as well fake something. So add some malicious transactions. Another is person who is the fastest. But in distributed network, how do we decide if someone is the fastest? No idea. In blockchain, people came up with the algorithm called proof of work. Proof of work means we give a puzzle for everyone in the network. Whoever is first to solve this puzzle can add their block and is rewarded 6.5 bitcoins. This puzzle needs to be complex, very complicated, and needs to give equal chances to anyone. So if I try to solve this puzzle randomly, I could be able, theoretically, to solve this puzzle faster than bigger player. And it happened multiple times that guy who was mining Bitcoin on his local machine accidentally mined a block because he guessed the solution for this puzzle. What this puzzle is? Let's imagine the string. Jacek sends 10 Bitcoin to Fuet. This is the hash of this string, of this transaction. If I add at the end of this transaction some string, like 1 to 3, I can find 0 at the beginning of the hash. So I can, this is some string. Jacek sends and Bitcoin, and we can see that with each letter I'm adding, each number I'm adding, the hash is changing. At some point, there will be 0 at the beginning of the hash. 1 0, it wasn't that hard. It took me 4 or 5 tries to find 1 0. To find another 0, it took me a bit longer to find 2 zeros at the beginning. The more zeros you have at the beginning, it's much harder to find this hash. And current difficulty is 19 zeros at the beginning of the hash. And probability of this number, this string, whatever we add to this transaction, that I find 19 zeros at the beginning, is 1 in 75 sextillions, which is 1 to the power of 10 to the power of 36, which means you need lots of power, lots of hashes, lots of tries to find this string. In Bitcoin, people came up with something which is called nonce, which is just a number. So you start from 0, then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on and so on, until we find this 19 zeros. This puzzle is adjusted based on the power of the network to keep the block frequency, so the time that the blocks are created, at 10 minutes. So if you take into account the network, the whole power in the network, new hash should be found only once in 10 minutes. Of course, it makes another thing. If I want to be faster than the network, I need to have more power and more luck than 51% of the network. So I need to be faster than the whole network to find these hashes faster and add my block faster. This keeps the network itself very distributed. So how the Bitcoin blockchain works, you've got these transactions. So from transaction 1 to transaction n, though there we create hashes of this transaction, then there is a whole tree of hashes, and we have a Merkle tree root hash. We have this hash. Then there is a timestamp of the block, a hash of the previous block, and then the nonce. Nonce is this counter. Whoever finds the number sends this block around the whole network to all participants in the network, to all other peers, and all other peers are checking. They are checking if this block with this number gives us 19 zeros at the beginning of the hash. If it does, it's super fast because it's just one hash, then this block is correct. Then they check the transactions. If the transactions are correct, which means no one spent more money than they actually had, and then this block is added to the blockchain, and we start mining and keeping the new transactions. Of course, there is more transactions that wanted to be added to the blockchain than there is space in the block. That's why miners, which are guys who are solving this puzzle, pick the transactions with the highest fee. Apart from getting fee from the network for solving this puzzle, they get fee for people to add their transaction. And this is a life cycle of the transaction. Transaction is created, signed by the owner. So I sign the transaction with my private key. Then it's validated. If the transaction is not valid, so I didn't have enough money, it's discarded. Then it's propagated, verified and recorded to the blockchain, confirmed and validated again, because we need to wait a few blocks until a transaction is considered valid. Do you have any questions so far? Guys, I can't believe I explained it properly.
Have you just chosen 19 only? Like,
Sorry?
there are 19 zeros only. Like, what is the relation for that? Like 19 zeros on the hash.
Why there are 19 zeros in the hash?
Yeah, because the possibility of the hash to be like if we have the first 19 zeros, then the remaining hash has the less permutations. Like after some time, like after millions of transactions, after millions of billions of transactions, like the hash can be repeated.
It's super hard because
if we are using 19 zeros, like around half of one third of the number
on the hash, and whatever I change, if I change a single bit in the beginning, I need to start from the beginning. So these are my transactions. If I change single bit here, I start guessing my hash again. So I start from 0. This is my block, and I start 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and I can do it randomly. 1,123, 500. There are different ways of guessing this hash, but but the proof of work is I need lots of guesses to, from this block, have 19 zeros here, or 10 zeros, or 5 zeros. And as you see, I didn't manage to find more than 2 zeros at the beginning, because it's really hard.
But like after some time, like when we are using this, after some time the repetition will be like, if the processing is such faster, and some of the hash can be same, like because half of the hash is 19 zeros, and other half can be the same for the other transactions. Or
yeah, half of the hash is 90 zeros. That's true, but since this is a hash function, so the basics of the function is that you cannot flexibly assign zeros in here. You need to guess it. You cannot. You don't have algorithm and way to guess those zeros. And whatever happens at the big end, those are some random letters. But since the hash is not reversible, I cannot take 20 zeros, have here 5, and start guessing those things, because I'm not able to reverse. Hash function is not reversible. Now I know what you meant. So since this is the hash, and this will be my zeros, and let's say ending is like that, and my block that I'm guessing is this, and I just need to guess this nonce. So the nonce is this counter that hashed with this whole block gave me this output. Since hash is not reversible, there is no way I can transform this into this block.
that I understand.
Because
But like
the nonce can be super long, and it's super long. It's something like that. And you need to guess all possible numbers to find this. And you don't know if it, and you can start changing these numbers. This to 2, this C to A, B to 1, this is hexadecimal, whatever. Hash function is one side only. You cannot reverse it. So you cannot guess this and have somehow this. That's the basic. That's why the cryptography works.
okay, like means what I was saying, like if we have 19 zeros, like some like okay, let me just confirm that.
And it grows exponentially. So 20 zeros is even more complex than 19. So the network will need to grow to all computers in the world to have 20 zeros at the beginning of the hash. But the basics of blockchain is, and hash function is that it's not reversible. So you cannot guess the hash, or if you guess the hash, you won't know what input created this hash. You remember because hash function transforms some arbitrary size input into fixed size output. but having output, you can never guess input. That's why to solve this puzzle, you start from input, you start from guessing these nonce, from guessing the numbers that will give you some number of zeros. And to check it, it's super easy. To check it, you just reverse it. So you take this and you take this and you hash it, and you compare the hashes. If the hashes are the same or not. But you can never guess if you don't know this. Only knowing the hash, it's not possible that you can guess that my name and these numbers created this hash.
Okay, thank you.
Okay, let's focus on the attacks. Since blockchain is a distributed network, what happens if either two people came up with the same hash at the same time, or we've got a country like Australia, there is a terrorist attack, and we cut Australia from the internet. This map shows the cables that connect different countries to the internet. So this is actual map. So these are actual cables under the Atlantic Ocean, under the Pacific Ocean, that connect different continents, different countries to the internet. And in Australia, to connect Australia to the internet, there are two places, here and here. If you bomb these two places, you basically cut Australia from the entire internet. And in case of distributed network, we've got a blockchain. So we add new blocks, we add blocks one by one, and then there is a terrorist attack. Australia gets cuts from the blockchain, but the miners in Australia mine the blocks. And miners in the rest of the world mine the blocks as well. At some point, in these blocks, there will be different transactions. Transactions can be in different order, which means the hash of the nonce to get this 19 zeros in the hash. So to solve the puzzle, this counter will be different for those two. So this block will be different than this. This block will be different than this. Australia will have internet inside of Australia, but won't be able to propagate these new blocks to the rest of the world. And I go to Tesla, and I send to the Tesla X number of Bitcoins to buy a car, or I buy a property using Bitcoin. And then we send the money, I got my car, or I got a notary permit to own a house, and then we come, the network, the problem is fixed, Australia got connected to the blockchain, and let's say Australia was responsible for 10% of all hash rate, which is the power in the network, and the 90% was in the rest of the world. 90% will come up with the new blocks faster than Australia, and the blockchain of the rest of the world will be different. What happens in Bitcoin network? We discard the blocks here, and we treat this as a proper blockchain. And this is called double spending, because I spent Bitcoin, bought something, but I didn't wait enough number of blocks. Something happened, and my transaction got reverted. And this is this double spending attack. That's why Bitcoin is not useful for payments, for actual stuff, because you need to wait a certain number of blocks, and I think it's 3 or 4 blocks until your transaction is can be treated as legitimate. Another type of attack is 51% of attack. Since this is all is based on probability, if I get over 51% of the network, I can do attack to rewrite the transactions. I can rewrite the transactions, modify them, and take over the power of the network. And as long as I got 51% of the network, I can take over the network. In case of Bitcoin, it's not possible because the network is too big. But there are many smaller blockchains, and these attacks happened already. Someone bought a massive AWS pool, got into the network, took over the whole got a lot of computational power in the network, solved puzzle very fast, rewrote the transactions, and sent himself 100,000 or from someone else's wallet transactions to his wallet. And as long as he's got power over the network, he could do that. So where we can use blockchain? In ransomware payments, so if someone hashed your drives and is asking you for ransom, you can pay him in Bitcoin or other cryptocurrency. Buying illegal stuff in darknet, investment. And one remark, guys. Don't treat this presentation, it's just only beginning, only like basic touch of blockchain. Don't think that after this this workshop you know everything and and you can start investing or using blockchain, because people make mistakes. And since blockchain is distributed network and there is no central bank, there is no institution where you can say, I made a mistake, can you revert my transaction? It's not possible. And there is an example of Reddit post where someone lost $500,000 by sending transaction to the wrong address. And if you do it, your money disappears. And if you send transaction to the wrong address or in the wrong way, in most cases, not only you won't be able to use it, but if you type address wrong, your Bitcoin and or Ethers cannot be retrieved. And this is just one of thousands of examples how people lost a ton of money. If you lose your private key, you can no longer sign the transactions. You cannot access the money in the blockchain. So this is very, very, very problematic. Fortunately, there are other blockchains, not only Bitcoin. There is Ethereum blockchain, where in Ethereum blockchain you can not only have transactions, you can have actual code stored in the blockchain itself. And you can execute this code. So far, do you have questions?
Yeah, Jacek, just a superficial question.
Yeah.
There is different kind of blockchain, like private, public, and hybrid blockchain.
Yeah.
So what is the difference from technical perspective between them?
So public blockchain is like Bitcoin. Anyone can participate. Private blockchain is we can create a private blockchain on our own machines and allow our own machines to participate in it. And the machines can work in one virtual private cloud or behind VPN, and then we can still have a blockchain, but this blockchain won't be visible and accessible by anyone.
Okay.
Hi, I have a question.
Yeah.
So since you mentioned this is a distributed network, so and everything in the example you showed, the one country got disconnected.
Yeah.
Which like what is mentioning if I make a transaction and at what logic we are getting like this peer was right with that like how to identify that my last transaction was correct and which would be added in the block.
You get information. So since blockchain is public, you can see what happened to your transaction. Let's send another transaction, and I will tell you step by step what's happening.
like who identified like my last transaction was correct and this would get added to a block?
I send transaction from wallet 2 to wallet 1, and I send those 10 ethers back. Then this is transaction. This is amount of ethers I want to send. This is a fee I will pay to the peers, to the participants of the network to send this amount of ethers. So this is a total price. Now I need to confirm this transaction. Confirming means I sign this transaction with my private key, and I send this transaction to the network, like in peer-to-peer network. I join the network and I send to the guys who are peers, who are miners, who have enough power to do these algorithms to verify my transaction. Add this transaction, and whoever add my transaction, they get this transaction fee.
Okay, and what in a scenario if my peer or my miner is got disconnected from the network, is disconnected from the blockchain?
Yeah.
Like the example of Australia.
Yeah.
So what would happen to my transaction if my peer is all lost?
It will be reverted. So let's. There are blocks, and someone got disconnected. So, or two miners come up with the same solution, and there are two different blocks with two different sets of transactions, and your transaction is here. Okay. So, for example, this is a case of Australia. You are in Australia. You send your transaction to buy a Tesla, but you are disconnected from the network, and then the rest of the world came up with this block.
Yeah.
Then the biggest block, and there is no your transaction, right?
Right.
The rule is longest blockchain wins. So if in Australia there is 10% of computational complexity, only 10%, and of the computational power of the whole world, and the puzzle, so this proof of work was set with current 100% to solve the puzzle once every 10 minutes, you will, in Australia, this puzzle will be solved one every 100 minutes. In the rest of the world, one every 9 minutes. It means that a frequency of the blocks is changing. So in the rest of the world, they will add more blocks, where in Australia there is still only one block. And when Australia gets connected to the network again, this block is discarded, other blocks are discarded because this block is longer. That's why I said, when you send a transaction, you should wait a few blocks, because there might be a case that that there are two miners who came up with the solution. They share the solution with the network, and whoever gets 51%, then other miners start to mine. Mine other blocks, and at some point, one blockchain will be longer, and whichever block is longer, so wherever there are more blocks in a blockchain, miners, and you as a peer, you got two solutions for the puzzle, you take the solution with the longer blockchain. That's just a rule. So your transaction will be reverted, and you will still have your money on your account.
Okay.
And
And is there any process to monitor this in a real-time scenario where like multiple instances are going off and you are getting long blockchains from around the world? So how this is all monitored, because there is no center structure here.
yeah, since it's public blockchain, the state of transaction, me sending 10 ethers to another address was pending. If I refresh it, transaction is successful. And I've got a number of blocks. See more details. Fee, nonce was 717 because this is test blockchain. So there are, I don't know, 4 peers or 5 peers in this network. So it's a very small network just for testing. And this is a block number. And since that, there are 16 blocks confirmed. So there have been 16 blocks after that one block.
Okay.
And you can see all the data in that one block. This is hash data in that one block. You can see details, and you can skip block by block. And there in the network, for example, 242 transactions in that block. Oh no, 50 transactions in that block. 67 transactions in that block. 46 in that block. And so there are best practices, like you should wait at least 10 blocks until you think that your transaction is correct. Because with the more blocks are there, since this is exponential growth, the higher probability is that there is no side chain that is longer than the one that you are observing.
Right.
Okay, let's take the example of Ethereum. This is a code. This is super simple code for storage. It's this is smart contract. Smart contract in Ethereum blockchain, apart from persisting in a blockchain transaction, part of in a block you can put as well a code. The code then will have their own address, and this code can be later executed. This is a simple, super simple storage. The code is compiled, and the code is deployed. This is address of this code in a blockchain, and I have here two functions: store, where I store the number, or retrieve, where I retrieve the number. When I retrieve right now, there is a 0, so there is nothing. I can store here 101. Store, transaction is stored. I can actually see the details of this transaction. Transaction in Ethereum blockchain is just sending a specific transaction to the address of this contract, where I specify dedicated inputs. And when I retrieve it, I retrieve 101 that was stored in that block in that contract. We can store here as well a text. Text. Let's add function store text. Text. So this is a function that will persist some string and assign this string from executing this function in this smart contract and store that function in the smart contract, and let's implement retrieve. Retrieve text. We need to return string. I'm not gonna explain what memory is. This is a very low level. So usually in Ethereum, we talk about low-level programming, which is equal to C or even lower. So we use bytes. We compile everything to the smaller. So we very rarely use strings. Let's compile that. Let's deploy that contract. And right now we've got two functions: retrieve and retrieve text. We can store here 1111. This is my number, and Jacek Janczura. This is my text. I can have as well access management, so allow certain addresses to access the blockchains, set owners, set the tables, set loops like for loop, and so on. What will happen if I write an infinite loop and trigger this transaction? Guys, how it works? I've got a code. I compile this code. I share this code and pay, of course, for keeping this code on all peers in the whole network. And whenever I trigger one of the functions in the smart contract, this function is executed on all peers in the network. Of course, I need to pay for it, and then a result is transferred to me, and the state is changed of the contract if I, of course, change the state, like persist a new string. What happens when I create a loop, infinity loop, and send this loop to the whole network, and then I trigger the function that triggers the infinity loop? The solution for it will break the network. So all peers will execute my transaction to verify that the result is the same as the guy who added new block to the blockchain. And these peers will be hanging on infinite loop. To break it, there is something which is called gas. Gas is like in car, we put gasoline to drive 100 kilometers, 5 liters. In here, I pay for computational complexity of my transaction. I pay in gas. There are fixed fees in gas for accessing, for persisting, for dividing, multiplying, subtracting numbers. So I calculate the cost of my transaction. I send it to the network, and as long as I have enough gas, this transaction will be executed. If I paid enough fees in this gas for executing transactions, transaction will be, and the result will be added to blockchain. If I don't do it, then and if I trigger this infinite loop, all peers will be stuck as long as I paid enough money in gas for them to execute this transaction. After 1 minute, all will be done. Of course, all will be paid, and I will just lose my transaction fees because the execution of my smart contract will be just timeout. And that's it. Thank you very much for your attention. Time for questions. Are you here with me?
Yeah. So, Anush, Shesh, Tomik, anyone has any question? Sandeep?
Like you
Hi Jack. So, like you mentioned, if we by mistakenly trigger an infinite loop, uh, then we might lose all our transaction and all the money gas that we have, right?
Yeah,
So,
yeah,
like,
yeah, yeah. It's
and
your
plus
risk.
our whole chain will be broken. So, like, we will be still be part of it, but we'll with no transaction money left, right?
Yeah, it's like you execute a function store name, and this in this contract there was a mistake. Someone created infinite loop. What will happen? I pay $1 to execute this function in this smart contract, and the peers are okay. I'm fine with it. And then they take your $1 and they tell you it wasn't enough to execute this transaction, timeout. And we persist in a blockchain timeout. You lose your $1 and that's it. And then in next, you need to either pay more or decide, oh fuck, there is a mistake, there is a bug in the code. I will no longer trigger this function in this contract.
Okay, so we can stop paying in middle, right? So
Yeah, 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 yeah.
okay.
Also, adding to this, like if someone intentionally try to block the peers, is there a way that a peer can get released, or somebody can stop the function?
No, and peers agree on that because they execute function as long as you put enough money. So it's
Yeah.
good for peer. Peers would be super delighted if you execute only infinite loops transactions because it means that they will only get a lot of money apart from fee because there is transaction fee to seed your transaction and there is a gas fee to execute your function. So it's perfect for them. Peers say, perfect, man. I'm super happy. 1 minute lasted, okay, or 10 seconds.
Yeah.
I'm out.
Yeah,
And
I just want to know if they want to disconnect from, or like they don't want that function to run.
yeah,
They don't have any control.
if you don't want your function to run infinite loop, then you need to correct your code. And correcting code is very complex in Ethereum blockchain because it requires you to deploy smart contract again.
Oh.
Any other questions? Okay, since there are no more questions, thank you very much for your attention. I hope you learned something about blockchain.